Okay, so this is the second session of the Phasor diagrams. The introduction, the last one, showed you how to form a Phasor diagram from a series of sine waves in a series circuit. So this time I'm going to concentrate on the resistor, inductor and capacitor circuits in series. So I'm going to start looking at where we finished off on last session. Okay, so we had the circuit in the top right corner there. So, and these are the waveforms we get from the circuit if we looked at using an oscilloscope. Across the voltage across the inductor would be this one here, which would be 90 degrees phase in advance of the voltage across the resistor. So the voltage here across the resistor, the voltage across the inductor, and the grey waveform is the current, which in AC circuits alternates between coming out of one terminal and then the other one. Okay, so if we now, so the diagram on the left hand side, the phasor diagram shown here, the phasor diagram is a rotating phasor, as we talked about, with a rotational angular velocity which is given by omega, rotates anti-clockwise, measured in radians per second. Bit of recap here. So as you can see, it's formed in a rotating circle like that. So if we now got rid of the messy sine wave graphs here, and this time we are just going to use the phasor diagram method to analyze the circuit across the way there. Right, so one easy way of remembering whether the inductor and the resistor and the capacitor are in relation, where they are in relation to each other, is to use the acronym CIVIL. Okay, so if we decided, if we've got an inductor and a resistor in the circuit, what we'd do is we'd circle this part of the acronym and we'd read from left to right, and we'd say that the voltage leads the current by 90 degrees. That is for an inductor. And if we were looking at a capacitor, then we would look at this side and we would say for a capacitor, we'd say, looking left to right, the current leads the voltage by 90 degrees. The resistor is always, for the resistor, the voltage is always in phase with the current. Okay, so we drew this out again. So let's say we have the current here. Just move it away from this circle, so the current would go that way. So the voltage across the resistor would go to the right like that. So this is your reference point. And for the inductor, as it says there, the voltage would lead, in terms of rotating this way, would lead the current VL by 90 degrees. And for the capacitor, we would have downwards, because the current in this case leads the voltage across the capacitor by 90 degrees. Okay, so that's a fairly easy way of remembering the relationship in the circuit. So if I move this down, and we'll go through an example. So if we wanted to work out, for example, we wanted to work out the equivalent resistance in an AC circuit for an inductor, well, the equivalent resistance in an AC circuit for an inductor is given the name XL. XL is called the inductive reactance, and there is a formula for XL, and is related to the frequency in the circuit. XL is equal to 2 pi FL, and we can derive how that has come about, this formula, but I won't do it in this session. So if we now go on to calculate what XL is, so it'd be 2 times pi times the frequency, which in this case is 50 Hertz, times the inductance, which is 10 times a milli, is times 10 to the minus 3. Okay, so, and if we calculate that, you would 2 times 50 is 100, 300, so 100, 300, and 0.1459. Okay, times 10 to the minus 3. Okay, so equals 3.159. And the units are ohms.